we're going to start to make a transition into a new topic here called number theory. We're really going to focus in the number theory is really the focus of the natural numbers. Okay, so we're studying the natural numbers, and we've seen a set of natural numbers already in our past studies of set theory. It's a set of numbers 1, 2, 3, 4, and so on. We start at the number 1 and proceed by adding 1, all right, indefinitely. So this set doesn't end. There's an infinite number of numbers in there. In fact, we would say that the cardinality, if you remember, the cardinality is infinite, and we say the cardinality of the natural numbers is Aleph naught, if you'll remember, if you recall that from our previous study of sets. And so number theory then is really getting into the natural numbers, okay, studying them, how they go together, how they break apart, that sort of thing. And so a couple things to keep in mind. We have operations with numbers, right? We add, subtract, multiply, divide, exponent, all those things. Well, addition and multiplication are very special operations with the natural numbers because they're what we consider closed. That means if you take two natural numbers and add them together, you get another natural number. If you take two natural numbers and multiply them, you get another natural number, okay? That's not the case for subtraction or division. Division, if you take two natural numbers and divide them, sometimes you get a rational number, like 1/2, that's not a natural number, right? Or if you do subtraction, you could do 4 minus 9, which is a negative number, is also not in the natural numbers. So addition and multiplication are kind of special when it comes to the natural numbers. And in our particular study, we're really going to focus in on the multiplication aspect. Okay, that's kind of the more applicable in terms of what we're going to be studying. So we're going to go into multiplication very closely. But here I have a description, the closed nature of those operations. A plus B, that quantity, A plus B, the sum, is a natural number. And A times B, the product, is a natural number whenever A and B are both natural numbers. Okay, so that's the description mathematically of that closedness of addition and multiplication. Now we'll get a few definitions in here, and then we'll start looking at some really interesting things. I love number theory. Some of the basics that we're going to introduce here with prime numbers and composite numbers, can't think of the word. Some of those things are going to be very profound and just interesting, I think. So kind of fun games that we play with numbers. And we're going to explore a lot of that in this coming chapter. And then, of course, we are going to get into some other types of numbers, not just the natural numbers, but in some sense, the natural numbers are sort of the building blocks for all the other numbers, using these operations, and then, of course, introducing subtraction and division to produce other numbers. Okay, so in some sense, that's true. Anyway, so let's say we just focus in on the multiplication side of things. If I have two natural numbers multiplied together, they give you another natural number, right? A, B, and P are all in the natural numbers. Remember this E symbol, I've got it listed up here a couple times, means element of, right? So we suppose that this product exists. Then A and B, the two numbers multiplied here, are what we call factors of P, and P is the product of A and B. Okay, so those are just some general definitions. You probably already know that. But that's important. And also, sometimes we'll use, instead of the word factors there, we'll use divisors, okay? Factors are where we're kind of looking at the multiplication side of things, putting things together. Divisors are where we're really focusing in on the final product and then looking at pulling it apart. They mean the same thing, it's just what context we're looking at. Are we looking at putting them together? Then that's a factor. Are we looking at tearing them apart? Then we're looking at divisors, okay? So we could also think of factors and divisors interchangeably because they really mean the same thing, they're just used in different contexts. Okay, Okay, but the product, that's just your final answer after the multiplication. Okay, then we would also say here that A divides P, and also B divides P. Now what does A divides P mean? Right, it's a divisor, so A is a divisor of P. If you were to think about division, then that means that if you were to divide P by A, you get no remainder left over, right? It doesn't create any sort of fractional part. And so you could say that A divides P means that the remainder to P divided by A is 0. Okay, so you have a 0 remainder when you do the division. Now, of course, that's really the only time that division applies to the natural numbers, because division is not really a closed operation. So we don't really want to work with division, at least in this initial sense. We don't want to work with division if I had 2 divided by 4. I would be okay with division as 4 divided by 2, at least right now. We start working with fractions and rational numbers, we'll start to incorporate a more broad description of division. Okay, so in our case, A divides P means that the remainder to this division is 0. Notationally, we would say that A, and then a vertical bar, and then P. All right, this is the notation for A divides P. Now, it looks very similar to a fraction bar, but it's not. It's actually the opposite of that in some sense. You would say here, for instance, that 8 divides 24, right? Because 8 is a divisor of 24. If you divided 24 by 8, you get a remainder of 0. Now, that's not the same as saying 24 over 8, right? These are two different things. This is saying that A divides 24. It's not saying what the result is. It's just stating the relationship between the two numbers. Here you're looking at a fraction, in which case you're looking for an answer for a result. These two expressions, though they look similar and though they are both using some sort of slash or line, are actually different representations. Okay, they really mean different things. Okay, so we're looking at the divisibility notation, something you may not have ever seen before. Okay, and of course we're sticking to the natural numbers. I don't want to include -8 here, something like that. All right, of course the remainder is 0 when you divide this out. Okay, now with the natural numbers, some numbers are divisible by other numbers. 4, for instance, is divisible by 2. It's also divisible by 1. It's also divisible by itself, interestingly. In fact, for every number, no matter what the number is, I'll call it n, is always a divisor of itself. N always divides n, right? A always divides A. 5 divides 5. 32 divides 32. Every number divides itself. And 1 will always divide a natural number, okay? So every number has 1 in itself as factors. Now the number 1 is kind of interesting because the number 1 kind of mends these two things together, so you really only get one factor of the number 1. In fact, it's the only number that has one factor, okay? Or one divisor. Okay, and now I'm speaking in terms of divisors. So let's take a look at that for a moment. So 1 is the only natural number with one divisor. everything else will have 1 in itself, and itself being different from 1 makes it 2 distinct factors. Now, many numbers have more than that, right? The number 4 has 1 itself and 2, okay? But 3 has just 1 in itself. That's it. And so we have a category, 2 different categories. There's the numbers that have, well, there's the numbers that just have 1 divisor. That's just the number 1. That's sort of set aside, okay? Then there's the numbers that have precisely 2 distinct divisors, okay? If they have 2 distinct divisors, they're considered what we call prime numbers. Now, as a definition then, I'm going to be very careful in how I word this. Prime numbers have exactly 2 distinct divisors. Okay. 2 distinct divisors. Namely, 1 in itself. Actually, I'll put a comma right there. Go to the next line. Namely, 1 and itself. Now, I specified this because exactly 2 means you can't have more than, you can't have 2 but then maybe some other ones, right? It has to be exactly 2 and they're distinct. So the number 1 doesn't work. You can't say, well, 1 is because it has 1 in itself, technically, but it's the same factor twice. Distinct divisors, okay? So the number 1 doesn't count because it only has 1 divisor. The number 2, well, that only has 1 and 2. That's a prime number. The number 3 has 1 and 3 as divisors. That's a prime number. The number 4 has 1, 2, and 4 as divisors, so it's not a prime number, okay? So prime numbers have exactly 2 distinct divisors, namely 1 in itself. The number 1 is the only natural number with 1 divisor. And then we have another category, 3rd category, called composite numbers. Now sometimes, just to be brief, we may say that that the composite numbers are everything that's not prime, but that's not true because the number 1 is also not prime, but it's also not composite. So what I want to say here is that composite numbers have factors other than 1 and itself. You could also state that another way, that it has more than 2 distinct divisors. So they have, oh boy, I can't write here properly. They have HAV more than 2 distinct divisors. Okay, the number 10, for instance, has 1, 2, 5, and 10 as its factors, so it's composite, as its divisors, I should say. Okay. Okay, so that gives you kind of an overview of the 3 different categories, the 3 main categories that we're going to study here in our first section on prime and composite numbers. Okay, we're going to go in depth in both of these. As far as we can within reason. We're going to talk about different divisibility rules for composite numbers to see what numbers divide them. If I had a number like 72, that's a natural number, and I want to figure out what other natural numbers are divisors. There are some kind of cool tricks to determining whether numbers are divisors or not. And it's quicker than just doing long division and figuring out if the remainder is 0. Okay, there's other really cool tricks involved that we'll get into in subsequent videos.